Welcome to my infrared astronomy channel for amateurs. My name is Andreas and I will talk you through an introduction, roughly 15 minutes, about infrared, its history, a little bit of physics, some gear and observation, mainly infrared sensors, and in the end a little bit of literature and a very short outlook. Infrared was discovered in 1800 by Wilhelm Herschel, or William Herschel, as you wish. If you ask me if this is the same guy who discovered Uranus, I'd say yes. What Herschel did is he was observing the sun with a telescope, a slit and a prism, and looked at the spectrum, and then, as you can see, he had a couple of thermometers and he noticed that beyond the red, the thermometer showed a bit of a higher temperature than the other thermometers. So he concluded there must be some invisible form of light there with a longer wavelength than red light. At the side of physics, there are two things we have to consider. One thing is the emission side and one thing is the absorption side of the infrared. If you have a black body, like for example a star, like our sun, it will emit light in a broad spectrum as shown here. For example, for the sun, the peak is in the visible range, and there's also some ultraviolet and infrared, and there's less and less light intensity the longer the wavelength is. So in near infrared you still have quite a bit, and in slow wave infrared and in the longer part of the infrared there is less and less light. That's something you have to keep in mind for later. This counts for a star of 6,000 degrees, and cooler stars have more part of the light in the infrared than hotter stars. And then the absorption side, what happens if the star or the sun is shining through an atmosphere? The gases in the atmosphere take out bites of the blackbody spectrum. Some molecules start working and absorbing depending on the bonds between the molecules, as you can see here. So in infrared spectroscopy, you can look which bonds are in the molecules and then try to find out more about the molecules. Two molecules very important in the Earth's atmosphere are CO2, carbon dioxide, and water. They tend to have very strong bonds and absorb a lot of infrared light, which finally leads to the greenhouse effect. People often think of CO2, but they think less of water and also methane when it comes to absorbing infrared in the atmosphere. If you're interested into infrared spectroscopy, I gave you two links here. One is Professor Dave and one is Chemistorian. They're better at explaining this than I am. This figure to the left you can find in some form in almost every astronomy book. The windows, you can observe the light from the shortest wavelength to the longest wavelength. Here it starts only at ultraviolet, but of course it's the same thing for X-rays and for gamma rays. The shortest wavelengths are just absorbed high up in the atmosphere by electrons, mainly free electrons. And then there's the optical window that contains UVA and a little bit UVB and the visible light and the near infrared. And then the infrared is a bit of a mixed shop. Parts of it are completely absorbed, parts come through quite well. And then there's a big gap here, and afterwards the micro and radio waves start, and they can partly be observed on the surface of the Earth. On the left side, the scale here was logarithmic, but here it is linear, so you can see the infrared better. Here there are a lot of peaks, and always one or two peaks belong to one wavelength range of the infrared. The near infrared is at the same peak as the visible light, and then the shortwave infrared has two peaks. The midwave infrared has a large and a small peak, and then there's this big gap, and then there's the long wave infrared. A big chunk of that is called thermal infrared, roughly between 8 and 12 microns. Now we come to the observation. I have to admit that I haven't done much observation so far because there are only limited ranges where there are relatively cheap sensors, and many of the sensors tend to be very, very expensive. But in the coming years, I hope that they will get a bit more easy to buy. One thing that everybody can do is observe with conventional CCD or CMOS cameras that are based on silicium. Many of these reach up to near infrared, at least 950 nanometers, 1000 nanometers. That's quite easy. Mainly the sensors that are used for planetary photography are good here, although it would also be good to cool them because the thermal noise gets more and more with longer wavelength. So that's a design choice that Sony basically does when producing these sensors. Either you take the infrared with you and you have more thermal noise, or you center the photoelectric effect in a way that the infrared is just cut away. This is, for example, one sensor I would recommend for infrared photography. It's a medium-sized sensor, the IMX664, but the 585 is practically the same in terms of sensitivity across the wavelengths, and this one is larger. And for the 585 there are also cooled cameras which are not don't exist, I think, for the 664 sensor. Recently there were some rumors about new CMOS cameras that can reach into the slow wave infrared until 1650 or something nanometers, but I haven't found any of them to buy yet. One of them are quantum dot sensors, and the others are also silicium-based CMOS sensors, like this Raven sensor. If anybody finds them to buy, I would be really interested. If we are at slow wave infrared, there are also the indium gallium arsenide, or just in short InGaAs sensors, like the Sony IMX 990 or 991, 992. But unfortunately, these ones are still prohibitively expensive, something like $15,000 for a quarter-inch or a half-inch sensor. But they're really the best what you can buy for shortwave infrared. As you can see on the picture here of the Orion Nebula, the sensitivity is very, very good, and you can see through nebula. And some people say you could even take pictures of the stars during the day. I would actually like to see that one day. This is an example of one of these cameras with one of these sensors, but as a cheaper variant, there are also line cameras that scan just two lines and shift them across the image. And these are quite a bit less expensive, something like $3,500. But I don't know to what degree they are really good for astronomy, because for a single line you have only a little time and then it scans again and again and again. There are also other types of sensors, but most of them are hugely expensive. And some of them are used for military, like the mercury cadmium tellurium sensor, which is also very, very sensitive, but I don't know if you can buy it as a private person, probably not. Or there are also these swap sensors, but I don't think that any of them are very practical for amateur astronomers. However, in the recent years there are colloidal quantum dot sensors, CQDs, and these are some compromise between sensitivity and price. But the cooled of these ones still would cost some $3,600 or so. For example, TubeTech makes these, also uncooled ones, which may be a little bit cheaper, but probably cooling is a good idea. And there are also sensors for long wave infrared. The cheapest ones are the vanadium oxide sensors, which are widely used for different purposes. For example, in architecture, to measure the heat that goes out of a house, like shown in this example with the door. And these ones you can also buy for your smartphone with a USB-C plug with quite a good resolution, and they should be able to see temperature differences of 35 millikelvin or something. And there is also this mini variant for drones, as shown in the example here, which makes it very easy to see warm objects like persons and cars. But the problem with these long wave infrared sensors are that you probably won't be able to see stars with them, because as we've seen in the black body distribution above, here the intensity at long wavelength is very, very low. For shortwave infrared, there's still enough if you're sensitive enough, like the InGaAs cameras. But for the long wave infrared with these polarimetric vanadium oxide cameras, the sensitivity is very low and probably you're not able to see stars unless you take a huge lens or integrate a very, very long time. Now I have some literature and an outlook. I can recommend you one book that is written by a professional for amateurs, the Infrared Astronomy Seeing the Heat book by Clements. I read it and it was relatively easy to read, whereas most books on infrared are really, really hard to read. And I also would like to recommend you my Instagram account that is given here. I will post my results there, but with if there's a procedure I want to show you, I will do it also here on this channel. My aim is to try various applications, maybe not only astronomical, but all of them infrared applications. Of course, I won't pay 15,000 bucks if I don't have them for a really sensitive sensor, but there are things you can do, I'm sure. And I will keep you posted if you're interested about any progress. Please like and subscribe, and it would be really great to find like-minded infrared nerds. Thanks a lot for the attention.